Now that we have our spatial polygon data frame created with our residuals stored in the data frame portion, we can now go through and calculate out Moran's I, which is a measure of global spatial autocorrelation. As we discussed in lecture, to calculate out Moran's I, we're going to need a spatial weights matrix. If we were looking at a points data set, we could calculate this matrix based on the distances between points. However, since we're working with polygons, we could do this with the centroid. It just isn't the best approach. So what we tend to do to create this weights matrix is actually look at polygons that share boundaries, or the contiguity between polygons. Now, we have the spatial dependence package, or SPDEP. That's going to give us a number of tools that allow us to create this the contiguity list and then process a weights matrix from that. So here we load the library, and then we create use the poly2nb function to create our neighboring polygon list. So we can take a look at that. Just kind of gives us some information on this neighborhood list object that we've created. We don't work with this directly, so we'll just move on. Here I can just plot, I'll just create a plot for you to visually see what this looks like. So here we have this polygon, and they're just represented by their centroids at the moment, saying we share boundaries here, 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 and here. So each of these other 4 polygons would be neighbors in the polygon neighbor list. Clearly it's quite congested on the west coast, so we can't see the specific connections. Now, the neighborhood list just is going to tell you which polygons share a boundary. To create the weights matrix, we need to modify this from those that share boundaries to weights. And the weights are pretty straightforward. For our example, if a polygon shares boundaries with 5 neighbors, each of those neighbors is going to have a weight of 1/5, or 0.2. We have 2 versions of the Moran's test available to us. We have an analytical solution through moran.test. Now, the recommendation is that unfortunately this test is somewhat sensitive to the form of the graph of the neighborhood relationships. So how are those relationships existing across space? How length of shared boundaries, you have edge effects. Okay? So it's actually best to use a Monte Carlo simulation approach through moran.mc. Now, in many scenarios, these will come up with the same result, but the authors of these tests recommend that we use the Monte Carlo simulation implementation in R. So we have to create our spatial weights matrix, and we use the nb2listw function, so the neighborhood list, to a spatial weights matrix, and we can do that on our neighborhood list that we created. So let's run that. We can see what that looks like, just give some information about it, talking about the weight style. We don't need to interact with that too much, so we can close that. If we want to look at specific neighbors, so for example, for polygon 20, we can look at the neighbors, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9 different polygons that has neighbors. And if we look at the weights, we can see that each polygon is given a weight of 1/9. So that is our weights matrix. So now we have that created, so we can run the Moran's I test. And for that, we need to specify our variable. So here, we will use the residuals variable and specify the weights matrix and just run the analytical version of the test. We see that our p-value is less than 0.05, which means that there is some statistical significance to our result. Our Moran's I statistic is positive at 0.525, which indicates to us that we similar values are located near each other. Now we can run the Monte Carlo simulation, and here we have 999. This is going to run 999 simulations. We can see if there is a default for that by looking at the help. And here that is nsim, and it is something that we need to specify. Okay, so here we've specified it 999. So we're going to run our simulation 999 times. We could run it further, and we come up with this very similar test statistic here, and that it is statistically significant. Now that we know we have a statistically significant issue with our residuals based on Moran's I, now we know there's spatial autocorrelation. We can't utilize the model that we created because we know it's invalidating one of the assumptions. We have two options to deal with this. Well, we have our first option, which would be to try and obtain a variable that we may have misspecified. So we may have excluded a variable that varies across space and is tied to that spatial autocorrelation issue. Or if we can't figure that out, we could look at using one of two of our spatial regression models, either the spatial lag or the spatial error model. Both of these are functions in the SPDEP package. And the lag model is lag SAR LM, SAR meaning spatial autoregressive model, LM linear model, it's extension of that, and then we're using the lag model. Okay. So what we need to do, again, is give it a formula. So we're giving it the same formula that we gave to our linear regression model. We need to now point it to that spatial polygon data frame because we need to use that data set. And then we need to give it a weights matrix here that we created. So here we can run our model. It's going to take a little bit of time to calculate. And then we can get details of it. Well, we can look at what our model output is. Now, these models aren't going to give us a R squared that we can use to compare the models, but we would use the log likelihood. And here we can get more detail, just like our linear model, by calling the summary feature. We're not going to get into interpreting this model here, but we can see down here there's a test for residual autocorrelation, and we see that we would reject that test. So our model has managed to get rid of the spatial autocorrelation. We can add our residuals from the lag model to visualize that, or test it using the Moran's test. So what we do is we call the function residuals, use our lag model object that we created, and here we have our spatial points data frame. We can add a new variable, lag resids. That's going to add it in, and then now we can call the Monte Carlo version of a Moran, and we see that we reject the null hypothesis. Or we do not reject the null hypothesis, we retain it. So we don't have spatial autocorrelation occurring in our residuals. For the error model, we just use error SAR LM as our function. We specify it the same way. So we can run our model there. We can add in those residuals to our spatial polygons data frame and calculate out the Moran's I there. And again, we see that we retain the null hypothesis and we have removed spatial autocorrelation in our residuals. Let's create a plot of those residuals to see what they look like using the spplot function. It's just taking a moment. And now we see more of a random pattern, as we may expect. And this is the residuals from our error model. Now, we discussed in lecture about the underpinnings of each of these models, and we talked about the way that we might be able to choose which model we might use. And so we have the Lagrange multiplier diagnostics test, And here we'll just split this up. So we will just save it as an object. So we will run our tests here. And so what it is, it's lm.lmtest. You give it our model. And this is our non-spatial model because we haven't done any of the spatial modeling usually when you use this test. We give it the weights matrix. So we'll need that spatial weights matrix. And then we tell it to use all of the tests. And from there, we can look at the summary. Now, this summary is not extremely helpful because how we read this is you read it from top to bottom, and you would see, look at the top two first, and you'd see, are either of these significant? And in this case, both of them are. And this one's testing, is it appropriate to use the spatial error model? Is it appropriate to use the spatial lag model? But what we see is both of them are statistically significant. What you would do next is look at the robust versions of these estimates. And in our scenario, again, both of them are statistically significant. If only one of them were statistically significant, that would then allow us to suggest that we use that particular model. So in this case, we would have to use some of that theoretical underpinning that we discussed in class about the differences between the lag and the error model in selecting your model. So that is it. So take this information and you'll be applying it for your assignment.